Okay, so does anybody remember what we're talking about?
Fourier Transform.
Fourier Transform, yes. So, right, there's this whole other area of Fourier analysis where you take your function and then you do the Fourier Transform on it. This is, roughly speaking, taking a function, and then instead of looking at the function, you look at the amount of each frequency. You look at the frequencies, and you say, like, how much of each frequency of your function you have. And so you can take questions about your function and then change them into questions about the Fourier transform. So this is something that's done in partial differential equations, for example. Where you take a differential equation and then you hit it with the Fourier transform. It turns into a question on the Fourier transform side. Maybe it's easier to solve in that world. You solve it there and then you flip it backwards to the original. Right? So there's always this sort of like going back and forth between your original function and then the Fourier transform world. And so what we're doing is seeing that all these results in Fourier analysis, which I think are often Fourier transform, it's on the real line, and most of the you can do all the theory in Euclidean space. But it's also possible to get these to bring complex analysis into it, and then get the results using complex analysis. And so that's the cool thing that's happening in this chapter. Right? We're going to go after the standard some of the standard results in Fourier analysis. We're going to get them using complex analysis, and then we're going to use them to imply results about complex analysis, about holomorphic functions. Okay, so this is kind of a cool section. Okay, and so what we finished with last time was this thing that said that if you have a function that's in f sub a, right? And remember, f sub a means you're holomorphic in the strip, and you've got a uniform moderate decay along every horizontal line in the strip, right? If you're in f sub a, then that gives you that the Fourier transform has to satisfy a certain decay, right? That it must decay like this for all b that are between 0 and a. Okay. Yeah. Right. So that the Fourier transform, being holomorphic, forces the Fourier transform to decay pretty quickly, right? And you remember I don't know if you remember the idea, but the idea of the proof was basically to take the expression of the Fourier transform and then shift it using contour integration, right? So we use the Cauchy integral formula to see that we can shift it down by b, and that basically immediately gave you the result, right? Because the Fourier transform, right, is the integral of f of x e to the negative 2 pi I x c dx, right? And then when you shift it, when you shift it, you say, okay, well, this is going to be f of x minus ib e to the negative 2 pi I x minus ib c dx, right? But when you then when you're estimating the size of it, well, this part is controlled by the moderate decay, right? So you get this a 1 plus x squared, right? That part is controlled by the moderate decay, and then this thing here, right, is going to give you e to the negative 2b 2 pi b c, right? Because the imaginary part doesn't matter, right? The imaginary, this x is not going to factor into it because the size of it, this e to the 2 pi I x c, the size of that is just going to be 1, right? And the only thing that matters is this negative ib, right? So you're going to get, right, positive negative 2, so negative 2 pi b c, right, d dx. Right, this thing pulls out, right? This thing pulls out, and then you get some constant times. You get some constant times e to the negative 2 pi b c. Right. And this was for the case. This was for the case c bigger than 0 when you shift it down, right? And then when you for the other case you shift up and you get the same sort of result, right? Right. So everybody remember this? So this is I hope this seems pretty straightforward to you. You know, the idea is shift down, right? The idea is simply use the Cauchy integral formula, and the Cauchy integral formula allows you to shift the line of integration down by b. Okay, and then on that line, the bound that you want, it pops out immediately. No.
Can the uppercase b constant depend on the lowercase b?
No, because this just pulls out, right? So the constant simply depends on the moderate decay.
But doesn't the constant of moderate decay depend on the lowercase b?
It doesn't. It doesn't, because remember that we assumed that the decay was uniform on each throughout every single line.
Oh, I see.
The A was uniform through all lines.
Oh, okay, great.
Yeah,
Okay,
this
that
A
makes
is
sense.
uniform. Yeah, good. Okay, so that was sort of like the first step in the direction that we want. So like relating the behavior of the Fourier transform with the holomorphicity of the function, right? So right now, the sort of holomorphicity implies the sort of decay. Okay, so there's almost no point in using this eraser. Okay, so right now we're going to go after a couple of the main results, fundamental results in Fourier analysis. The first one being the inversion formula. Okay, so our theorem will be that if f is in one of these f sub a classes, then the inversion formula holds. So then inversion formula holds. In other words, you can recover the function from its Fourier analysis, from its Fourier transform, by doing what's called the inverse Fourier transform on it. Okay, right. Integrating the function against e to the negative 2 pi blah 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 is the Fourier transform. Integrating it against the positive is called against the e to the positive thing is called the inverse Fourier transform. So we do the inverse Fourier transform on the Fourier transform, and that recovers the function. Okay, that's what the inversion formula says. Okay, so here's the strategy. Strategy is pretty similar to what we did before. We're going to use the Cauchy integral formula and shift the lines. Okay. So suppose that let's say that f is in some f sub a, and let b be between a and 0. So what we're going to do is we're going to create a contour gamma sub r, just like we did before. So it's the rectangle going from negative r to r and from negative ib to positive ib. Okay. Okay. So, as usual, oriented positively. And what's the point? The point is that we can do the Cauchy integral formula on this, right? So by Cauchy integral formula, we have that for x in R, f of x is going to be 1 over 2 pi I f of zeta minus x d zeta over that for sufficiently large R, right? So take some real x, and then take R big enough that x is contained inside there, and we can use the Cauchy integral formula on it, right? Because we assumed that this thing was holomorphic in a strip that contains this box. Right. Okay. We're holomorphic in this whole strip here, right? So we can use the Cauchy integral formula. So far, so good? Yep. Everybody okay? Okay, so I'm not gonna go through the. I'm not gonna do the detail. I'm not gonna do the detail, but in exactly the same way as before, we see that that if you integrate over these, that the integral over these edges, over the vertical edges, goes to 0 as R goes to infinity. Okay, it's exactly the same calculation as before. So, as before, the limit as R goes to infinity of these things over, let me call this I negative R and I positive R. The integrals over I plus or minus R, these integrals all go to 0 as R goes to infinity. And that's just as before because of the moderate decay, right? We have the decay of F. So I'll just leave that as an exercise. Okay. So what does that tell you? That tells you that f of x can be expressed as, as the integral over this line down here, plus the integral over the line going this way. Right. The line at b going this way. So let me call this line negative b and call the upper guy line positive b. So line negative b and line positive b. So that tells you that that tells you that f of x equals the integral over line negative b plus the integral over line positive b. Okay, and this is maybe let me write it like this minus that, and think of the lines as being oriented from left to right. Okay, so if we think of both lines being oriented from left to right, then this is the negative integral. Is that okay? I'm not doing it. Are you happier this way? We can however you want to think of it. It doesn't matter. Okay. Is everybody okay? Yep. Okay. Okay. So okay. So okay, so here's the claim that the integral over the lower line equals the integral from 0 to infinity of the of half of the half of the formula. Okay, right. We're hoping we want to show that f of x equals the integral from negative infinity to positive infinity of that thing. And what we're going to show is that this is one half of it, and then this is the other half of it. Okay. Okay. Yeah. Similarly for L positive b. Okay. And so what we do is we say, well, if you look at the right-hand side, right? The right-hand side is this guy. Okay, we're gonna take the expression for the Fourier transform and just write it out. Right, it's gonna be the integral du fu e to the negative 2 pi I u c du right, over r times e to the 2 pi I x c dc. Okay, so all we've done is expand out the expression for the Fourier transform. Are you guys okay? Kai, what's wrong? You don't look happy.
No.
Did I do something wrong?
No.
Usually it's when I've done something wrong.
No, I was trying to figure out why, because we're inputting c into our f hat, but the c is still in the exponent. We just also pick up a u from the integral.
Yeah.
Okay,
So
okay.
right. So think of it like this: the c tells you what frequency you want to pick up. Okay.
Right.
So you're going to integrate this guy with the c here. This is basically specifying the frequency.
Mm-hmm.
So you'll pick off this is like the anti-frequency, right? And that'll allow you to pick off the coefficient for this thing. Okay. So yeah, so the c is here, right? Just like, well, no, forget it, just like nothing. Yeah, the c is up here. Okay, and then you integrate over the variable. Okay, right. The Fourier transform, of whatever is you take your function, you integrate against e to the negative 2 pi I this times x dx. Okay. So this x is just some dummy variable. Okay. Here we've had a dummy variable. Yeah. Okay. So So we play the same game as before, and we do another shift. We shift this integral down by b again, by b, and we get f u minus ib e to the negative 2 pi I u minus ib dc du e to the 2 pi I x c dc. Okay, and at this point, I'm afraid we sort of pull out something that we haven't really mentioned before, but Fubini's theorem, which says that under certain conditions, then it's okay to switch the order of integration. Okay, that's not always true, but in this case, it's okay. So sorry, we're just going to pull this one out. Later, we're going to pull another thing out of the hat as well, something called dominated convergence theorem. But sorry, we just need to pull that one out. It's okay to switch the order of integration. So we're going to integrate over xc first, and then u. So this thing doesn't depend on, this thing doesn't, this f sub f of u minus ib doesn't depend on xc, so we can pull that out, right? And we're left with e to the negative 2 pi I e minus ib, e to the 2 pi I x xc. So let me just add that on. So plus xc. dxc.
Why is there an extra DC on the second?
So this should be a minus.
Minus
Oh,
three.
yeah, what is that? Hold on. That's just a C, sorry. Thank you.
Yeah, I was looking at that for like 5
Thank you.
minutes.
Thank you, Justin.
Okay, cool.
Okay. Good. Excluding the massive cheat that I've put in here. Yes, Jan.
Does that mean that there would be an extra c in the
Yeah.
exponent in the last?
Extra C in the exponent. Yes, thank you. Yeah. Yes. Yes. Okay. Any other corrections? About a year ago, I went to my doctor and I said, I keep on forgetting things. And he gave me a referral to a neurologist. But then I lost the referral to the neurologist. And my younger brother said, that was the test right there. Right, yeah. Yeah. Okay, so yeah, don't grow old.
I know everyone.
Yeah. Okay, so at this point, there's a small calculation here. So here's the lemma. That if you have a bigger than 0 and b some real number, then if you're integrating from 0 to infinity, e to the negative a plus ib c dc, that's 1 over a plus ib. Okay. I'm not going to do it. It's just calculus. Okay. It's just elementary calculus. But what that gives us is that that expression at the bottom there equals the integral of f u minus ib. Then we get 1 over 2 pi b plus 2 pi I b minus x. Right. Right. Yeah. So that, I believe that's what we get. Okay. So we get this. Okay. But what's that? That's, if we factor out a 2 pi I out of the bottom here, we get f of u minus b over u minus, I'm sorry, that should be u minus ib, f of u minus ib over u minus ib minus x du. Right, over R, right? And that is exactly what we wanted, right? That is, that's this. That's 1 over 2 pi I integral over the lower line. That's just the concrete version of that. Okay. Okay, so that's half of it, and then the other half of it would be, you know, you do the integral over the upper guy, and you get the other integral. That's basically the same argument. Okay, any questions? Okay, the next thing we're going to do is the so-called Poisson Summation Formula. So this is another kind of you know, significant result in Fourier analysis that has applications in number theory, as well as in other areas. We're going to prove kind of a limited version of it, but the Poisson summation formula for us will be this: you have some function that satisfies our, you know, that lies in one of the f sub a's. In that case, the sum of the values of the function at the integers is the same thing as the sum of the values of the Fourier transform at the integers. Okay, and we're going to prove this by changing this into a statement about integrals using the residue theorem. Okay, so the trick is to use the residue theorem. Okay, so here's the observation. Observe, if you look at the function 1 over e to the 2 pi I z minus 1, okay, then this thing has simple poles at the integers. Okay, right? You know, this thing, you know, is going to be 0 at the integers. And if you look at this thing, it's got simple 0. It has simple the denominator has simple zeros at the integers. So this reciprocal is going to have simple poles at the integers. Okay. And if you calculate the residues, with residues, they're all 1 over 2 pi I. So maybe exercise. Okay, so then if you take our function, then f of z over e to the 2 pi I z minus 1 will also have simple poles at the integers with residues f of n over 2 pi I. Okay. So now we're going to use the residue theorem on this guy. Okay. And we'll just like sum up all the poles. and that will give us an expression for the sum of all the integral values at the integers of f. Okay, so this is pretty cool, cool idea. So take a rectangle. The left-hand side is at negative n minus a half. The right-hand side is n plus a half. The lower part is at negative IB. The upper part is at IB. Okay, and we'll call that, as usual, gamma sub n. Okay. Then, so define gamma sub n as the curve around this rectangle. Then, by the residue formula, we know that that 1 over 2 pi I times the integral of our function e to the 2 pi I z minus 1 dz over gamma n is going to be the sum of the residues at the sum of the residues of f. No, of this function. I don't know. Let me call it g. Right, at the integers n where the size of n is smaller than capital N. Right, that's just the residue formula. Yes. Okay. So we already know that those guys are 1 over 2 pi I f of n, right? Right, and so that tells us that what we're really interested in is the limit of this thing as n goes to infinity. Right. This is the integral we want to deal with. Okay. So again just as before. So similar to before, we get that that the sum over, we let capital N go to infinity, and we get that the sum over all the values there is going to be the integral over the lower guy plus the integral over the upper guy. So just like before. Okay, and so what we're hoping is that this thing will equal the sum of the Fourier transforms values. Right? That's our goal, to show that those integrals equal the sum of the Fourier transforms. Everybody all right? Okay, let's go on. So, let's show that. Let's prove that. Let's prove that question mark thing here. This thing. Okay. So what we're going to do is we're going to write the sum over all these guys. We're going to break it into two parts. The sum of f of n plus 1 as n, the Fourier transform at n plus 1 as n goes from 0 to infinity, plus the sum of Fourier transform at negative n as n goes from 0 to infinity. Okay. Right. And what we'll see is that this one equals the first integral, and then the second one equals the second integral. Okay, so let's just write down what this means. Right? This is the Fourier transform at n plus 1. So this is the summation n equals 0 to infinity, the integral over r, f of, we can call it x, yeah, x, f of x, e to the negative 2 pi I n plus 1 x dx. Right. That's the guy on the left. We get summation from n equals 0 to infinity, f of x, e to the 2 pi I and x dx, for the guy on the right. Okay, so that's just by definition. Okay, so we're going to do something similar. Sorry, I should have said something before. So let say that f is in f sub a, and that b is smaller than a and bigger than 0. So we're going to play the same game as before. We're going to shift the contour by b. We're going to shift this guy's contour by b down. We're going to shift this guy's contour by b. Oops. Nobody caught my mistake. Yeah, there should be an integral there. Okay, we're going to shift this guy's contour down and the other guy's contour up. Okay. So again, so shifting contours. We get summation b integral over the negative b line plus the integral over the positive b line. Okay, so at this point, we play a trick, which is we say, well, look, on the line negative L negative B, e to the 2 pi I z is bigger than 1. Right? Because this e to the 2 pi I z is going to be e to the 2 pi I x minus ib, right? X minus ib. And so we're going to get e to the 2 pi b, right? E to the 2 pi b, which is bigger than 1. Okay, and so and for things that are bigger than 1, we have this expression 1 over w minus 1 equals 1 over w times 1 over 1 minus w. We've used this sort of expression, equals 1 over w, 1 over w to the n as n goes from 0 to infinity. right? We're just using the geometric series, right, where W is bigger than 1. Okay, right. So what's the point here? That we can using the uniform convergence of the series. Using the uniform convergence of this series, we can bring the sum inside, right? We can switch the order. We can switch the integral and the sum, right? Because of uniform convergence. Okay, so what it'll give us, that thing on the left is going to be the integral of f of x against 1 over e to the 2 pi I z minus 1. 2 pi I, sorry. I should call this z, sorry. Saving x for real numbers. Right. Yeah. Okay. And then you do something similar on the other guy, right? And you get the integral of you do something similar, except on L sub b, this thing is less than 1, and then you use that. You use the corresponding formula. So, okay, and that's it, right? This is what we wanted. We wanted to show that. Remember, we took the Fourier transform. I'm sorry. We took the sums of f at the integral values, and we got this thing. And we wanted to show that this thing was equal to the sums of the Fourier of the Fourier transform at this thing, at the integers. So that's it. Right. Express this thing, spell this thing out as in terms of the Fourier transform, right? And then shift the switch the order of switch the sum with the integral by uniform convergence, and that gives it to you immediately. Okay. So I only did this left half, but again the right half follows in the same way. Okay, so just think, what did we use? We used the residue theorem, right? And then we used the Cauchy integral formula to shift the contours, okay. And that's it. Okay. Yeah, this is mainly a residue theorem application, and really cool. Okay, you guys all right? Any questions? When I first interviewed at Scripps, they had me do a job talk, and I gave the job talk. I had to give a lecture to like some sophomores on the chain rule or something like that. And I actually went through the proof of the chain rule, which is probably a mistake for a calculus class. And I said, any questions? And then I waited for 10 seconds, I think. Maybe it was like 20 seconds. And apparently, like, the people who were watching me were just freaking out. Like, he's waiting so long. How is he waiting so long? But right, because most of the time when people ask, are there any questions, they don't wait long enough. Right, so I feel like you should wait an unusually long time. Okay, let's go on. So now we're heading towards like the big result of the chapter, which is the Paley-Wiener theorem, right, which relates the support of the function, right? When we say the support of the function, we mean the place on which the function is non-zero, right? So the support of the function to the decay of the Fourier transform. Right? So this is pretty cool. Okay, so here's the first result in the direction of the Paley-Wiener theorem, which we're not going to even state today. Actually, let me just say it on the side here. So here's what we're heading towards, the Paley-Wiener theorem. Says, if you have a function that's continuous and of moderate decrease, then the support of the Fourier transform is contained in some interval negative m, if and only if f has an entire extension. Right, so it can be extended to the complex plane so that it's holomorphic in the whole plane. Okay. F has an entire extension that satisfies a certain growth condition that grows like this. Okay, so this is an if and only if condition. Right. If your function grows faster, cannot be controlled like this, then that tells you something about the support of the function. Right. Okay. Like how big, where the function's frequencies are. And this is sort of saying that in terms of frequencies, there's a cutoff, right, beyond which it has no frequencies.
Is it usually easier to show that it has an entire extension than to show that the support is contained in this compact set, or is bounded directly? Because it seems like this entire extension is a difficult condition to prove.
Yeah, I guess the point of interest is that there is this relation at all.
Okay.
Right. Yeah. Not that you want to check this in this way, but rather that isn't it interesting that the support of the Fourier transform is related to the growth of the system. Yeah. Okay. So let's get something sort of heading in that direction, which is sort of the opposite of the thing that we mentioned at the beginning, right? Right at the beginning, we said that if you are, in this class f sub a, then you satisfy certain decay, right? Then your Fourier transform satisfies certain decay. And what we're going to say now is kind of the opposite. Okay, so if there exist a and capital and little a positive numbers such that the Fourier transform satisfies that decay, a capital A e to the negative 2 pi a x c. Then, for all b such that b is between 0 and a, f is the restriction to R of a function holomorphic in S of B. Okay, and we're going to assume for these results that that the inversion formula holds. Okay, so assume that the function satisfies conditions that imply the inversion formula. Yeah, whatever condition you want. Just assume that the inversion formula holds. Okay, so if we satisfy this decay, then we must be the restriction of a holomorphic function. Okay, that's what this is saying. Okay. So the proof is, well, we're just going to make the extension. So we create the function, whose restriction f is, right? And we do it using the inversion formula. We say, so extend f to S sub b z in S sub b via the definition f of z is just going to be the integral over R f hat c e to the 2 pi I c z dz dx. Excuse me. Okay, so at this point you should sort of be like, what? what are we doing? So, but at least for one thing, you see that if we did this, if we replace this z with x, then this thing on the right would be the inversion formula, right? And then that would be true, right? F of x is going to be equal to that thing, right? So notice that on the real line, this is f of x, right? Because this expression on the right, by the inversion formula, is f of x. Okay. So, but you need to be a little bit concerned. Like, does this integral even make sense, right? So notice that this integral converges, right? Because of our assumption, right? Because of our assumption, right? If we look at this integral, we see that this thing is controlled by, we've got this a e to the negative 2 pi a absolute value of c. We also have this. We also have this thing here, right? But z, remember, is x plus. Oh, sorry. The imaginary part of z is smaller than b, right? Because our b was in the strip, right? I'm sorry, our z was in the SB strip, right? So the imaginary part is between negative and positive b, right? So that tells us that the size of this thing, right, is at worst e to the 2 pi I absolute value of c times b. Right. So this is the bound for the modulus for the absolute value of this, right? This thing at worst is this big. Right. The biggest thing we're going to get for the imaginary part of z is positive b, right? And the biggest thing we get for c is the absolute value of c, right? So we just put in the biggest things possible. That's the upper bound. Right? But right, that's you get this a e to the 2 pi right 2 pi b minus a c c, right? And a is bigger than b, right? A is bigger than b, so this converges. Right? We're integrating something with a negative. We're integrating a decreasing exponential function, right? Which certainly converges. Okay. The point of that is that this integral actually makes sense. Okay. So right. So, but we said that we're going to have a holomorphic function. Why is this a holomorphic function? We don't know, right? We haven't proved that yet. We have 3 minutes. And that's plenty of time. Okay, so y is f holomorphic in S of b. Well, let f sub n be the truncation of this expression. Okay, so we're going to take that thing and we're going to truncate it between negative n and n. Okay, so right, we're basically what we're doing, in some sense, is taking the function's Fourier transform and then just chopping off its frequencies, between these in this range, and then we're inverting that thing back. Okay, that's what's going on here. Okay, so okay, and observe that these f sub n are all holomorphic. Why? Because these are those averaging integral expressions that we had before. Do you remember? You have some holomorphic functions. They're continuous on some product domain. You take the average, and then the thing is holomorphic. Right? This is using that theorem. Right? So these guys are all holomorphic. Okay. Right. Okay. So. Right. Okay. So the claim is that on S sub b, the f sub n converge uniformly to f, right? And then that will do it for us because we've got uniform convergence of holomorphic functions to a holomorphic to a function which must be holomorphic. Okay. And what's the point? The proof is that, well, you say, well, look, if you take the difference between these two functions, well, that is going to be controlled by, what do you get? You're taking f is the integral over r, f sub n is the integral over this interval around the origin, right? So the difference is just going to lose the part near the origin, right? And so we're going to get this thing. So this is going to be the integral, right, outside of negative n of this thing. Right? Because we're subtracting off the part inside there, and so we get just the difference, right? Okay, and then we run through the same thing as before. We get that bound over there, right? So we get the integral from for c bigger than n of e to the 2 pi I b minus a c e c, right? But this integral goes to 0 as n goes to infinity, right? This thing, you got this huge decay on the integrand, right? You got this decay on the integrand. As n goes to infinity, well, this term on the right is going to go to 0. Right? So this goes to 0 as n goes to infinity. Right? So we can make the difference between f and f sub n as small as we want. Right? In other words, we have uniform convergence. And so we're done. Okay, that's it for today. Unless you guys have questions.
On the right side?
Yeah.
It's a little bit further behind, but isn't it supposed to be made 2 pi I A C? Or there's no I there, so I was kind of wondering like what happened to the I.
The I, you see, when we we've got this e to the 2 pi I cz, where z is x plus iy.
Oh, that's what
Right.
happened. Okay.
Then the terms that the e to the imaginary exponent are just going to vanish, right? When you take the size, that part vanishes, and we're just left with the 2 pi negative y c. But that is controlled by this.
I see.
We take the right, c is smaller than absolute value of c. Y, whatever negative or positive, y is going to be smaller than plus b.
Yeah. Okay.
Positive b.
That makes sense.
Okay, that's it.
Thank you.
Thank you.
Next time, Paley-Wiener theorem. Look forward to it.
Next time to what?
Next time, Paley-Wiener theorem. Look forward to it.
A bit louder.